Welcome back all of you. In the last class we discussed about Cauchy sequence, the phases of the diagonal peaks and cross peaks in the conventional 90T1 90T2 Cauchy. We understood diagonal peaks are always in phase and cross peaks are anti-phase in both T1 and T2 dimensions. As a consequence, and also we see diagonal peaks or if they are very strong, it gives rise to tiles and mask the peaks which are close to its close to diagonal, and it has to be always represented in magnitude mode, and it gives like a star like structure especially for all diagonal peaks and cross peaks, and it is not suited for high resolution. We also understood about took the example how to use the Cauchy especially for identification of the immediate coupled neighbors. All those things we discussed. And another variant of the Cauchy is the double quantum filtered Cauchy. It is a 3-pulse sequence. First 2 pulses are there. First pulse always creates +1 and -1 coherence. Second one always can create multiple quantum coherences. And we know we can put a multiple quantum filter, choose the pathway from +2 to -1 by using either phase cycling or the gradients. And then we found out both diagonal peaks and cross peaks are antiphase in character here. And we can represent the spectrum in double absorptive mode. It is better for high resolution, and you will not get into the structure like strong peak which is masking diagonal peak which is masking the peaks close to it. All such problems are not there. We took the example and compared one of the samples for both Cauchy and DQF Cauchy. Fantastic resolution you could see for the DQF Cauchy. Another advantage is you can filter out all the singlets, uncoupled protons, solvent, reference, everything which is there can be filtered out because you are going it through a double quantum filter. They are all uncoupled singlets. So as a consequence we can filter it out. So there are several advantages, and conventionally nowadays you need to use only DQF Cauchy. Cauchy is not necessary, it is only for understanding purpose. The representation and better clarity, better resolution, everything you can get better in DQF Cauchy than conventional Cauchy. So this is one of the variants we discussed. Today we will go further and see another 1 or 2 simple variants, and then quickly without going into the details we will go to the other experiment because we do not have much time, and then with only a few more classes left we have to complete the course. So what I will do is I will quickly show you what is a Cauchy 45 sequence. It is another sequence where the second pulse is 45 degree. In conventional Cauchy this is 90, this is 90, but in the Cauchy 45 this is 45. Here advantage is the intensity of the cross peak near the diagonal becomes smaller and the diagonals become narrower. That is one thing, and the cross peaks appear tilted. The tilting of the cross peak gives you the information about sign of the coupling depending upon the relative the slope of the displacement vectors of the cross sections, or the slope in which the peaks are tilted, cross peaks are tilted. We can get the relative signs of the spin coupling constants. This is another important thing which you do not get in the conventional 1D NMR. Look at it, this is the simple spectrum of some molecule, you do not have to worry. The conventional Cauchy 90, this is Cauchy 45. Look at here, especially this region cross peak, look at this one. Some peaks are missing. Nevertheless, you see this appears tilted here, whereas this appears tilted here. It will show us, give us some information about the sign of the coupling. The direction in which it is tilted, that means this slope is negative, this slope is positive. I can say the coupling, if you get some value of the coupling for this and this are opposite in sign. So we can get the relative sign. Of course, I am not talking about the absolute sign, you cannot get it, but the relative sign of the coupling can be easily obtained. So for example, in this case vicinal couplings are usually positive and geminal couplings are negative. So as a consequence you can see this is geminal, this is vicinal. So from this you can easily find out sign of the. Of course we have the idea geminal couplings are always negative and vicinal couplings are always positive. So if you consider this tilting negative sign as positive, then this is negative. Like that we can get the relative signs of the coupling. Okay. So this another experiment called long range Cauchy. It is also called delayed Cauchy, delayed correlation spectroscopy. What we have to do is the same 90 T1 90 sequence, but in before and after the second 90 pulse a small delay is introduced. This delay pertains to 0.5 divided by j. The advantage is additional fixed delay before and after enhances the evolution time while retaining the same digital resolution. That is another thing. It is as good as telling you have enhanced the digital resolution. What does it mean? You get better resolution. Small couplings which you cannot get in the conventional COSI, you can get it from this long range COSI. So, it will allow small spin coupling constant greater than 4 bonds or 5 bonds away, 2 protons which are coupled, which are separated by more than 4 or 5 bonds, which was difficult to detect in a conventional COSI, you can detect from the long range COSI, also called delayed COSI. So, that is a biggest advantage. Of course, how do you set the delay? It depends upon 0.5 by j, and you have to approximate, you take some average value. This is a simple spectrum of this molecule. Look at it, this is a COSI 90, this is a delayed COSI. Can you see additional peaks here, which you do not see here? This is the advantage of the delayed COSI. The correlation to the small long range couplings of up to 1 Hertz, around 1 Hertz, are not seen here in the COSI, here and here. See, this is very small correlation is there between this and this, which is not seen here, but you can see that in the delayed COSI. That is an advantage. Okay. So, I mean, you can, there are so many pulse sequences designed for the variants of COSI, like soft COSI, small flip angle COSI, AE COSI, exclusive COSI, varieties of things are PE COSI, all are variants of the simple 2 pulse sequence. We do not need to go through all through these sequences, but simply remember all these are improved versions to circumvent some of the problems which are inherently present in the 2 pulse 90 T1 90 90 T2 COSI sequence. Okay. So, with this now we will go to the next another experiment called TOCSI. TOCSI means total correlated spectroscopy. The name clearly tells you it will identify all the coupled spin systems in a single experiment. It establishes connectivity among all the coupler partners of a spin system. Remember, I told you what is a spin system? You can it is a coupled group of spins where one is coupled, other is coupled, all of them are coupled among themselves. One of the coupling may be 0, does not matter, but they should form a coupled spin system, part of the coupled spin system. Then it will see that polarization transfer takes place among all of them and establishes connectivity among all the coupled spins. COSI establishes connectivity to the immediate neighbor, whereas TOCSI establishes connectivity among all the coupled partners of a spin system. So, what is a TOCSI pulse sequence? This is a simple 90 T1 isotropic mix in TM and FID. It is a very simple experiment and similar to COSI sequence, but only thing is this of second 90 pulse you are going to have a broad isotropic mixing pulse. It is called spin lock pulse. It is used for isotropic mixing called spin lock. This is a pulse. It has the pulse width could be of the order of milliseconds, several milliseconds. Okay. So, what is happening in this case is bring the magnetization from z axis to y axis by a 90-degree pulse. Immediately you can apply a pulse along y axis, RF pulse. The B1 field now is along y axis where the main magnetization is also there. Then what happens is the vector gets locked along the B1 axis. That is why it is called spin locking. The spins are locked along the B1 axis. Okay, that is what happens. How does this spin locking works? It is a continuous pulse. As I show you here, it is a isotropic mixing, a wide pulse of order of several millisecond. Then how do you understand the working of the spin lock? We will divide this entire continuous pulse into number of spin echo sequences like this. You all know it is a spin echo sequence, delta 180 pulse delta, it is a spin echo, another delta 180 delta, another 180 delta 180. So, what you can think is, you can think this as a single long low power pulse of constant phase. You treat this as a continuous sequence of closely spaced 180 pulses, closely spaced 180 pulses bracket by infinitely small periods. So, 180 pulse period, small period, 180 pulse small period, like that you can treat it as if there are infinite number of spin echoes in the entire continuous pulse can be treated like infinite number of spin echoes. So each delta tau period constitutes homonuclear spin echo. You can treat like that. It is not exactly like that. There are no gaps, there are no delays like that. But it can be treated, and if you take infinite like that, it appears like it is continuous. Okay. So the 180 pulse, what does it do in the spin echo homonuclear case? We discussed this during product operators. It refocuses the evolution of chemical shifts. That is what 180 pulse does, and there is no chemical shift evolution during this delay, and you are going to have all the spin vectors along y axis. Why? There is no chemical shift evolution, there is no offset, there is nothing, it is not going to evolve. The spins always get locked along y axis. That is why it is called spin locking. They remain along y axis, along the direction in which you are going to apply the RF pulse. So that means this 180 tau sequence, now we have treated for the entire mixing period as infinite number of such spin echoes. So you can treat that the spin vectors completely set to be spin locked in the rotating frame. When you bring the magnetization to XY plane, we are already thinking about rotating frame. This we discussed what is the rotating frame, everything in the previous course. So I am not going to touch upon that. Those who are interested, you can go back and look into that. So the spins are locked along the B1 field in the rotating frame. So during the spin lock, this thing, protons experience the same effective magnetic field, all the protons, irrespective of their chemical shifts. They experience the same effective field and hence the same chemical shift offset. What is that chemical shift offset now? It is 0. That means all protons has experienced 0 chemical shift. There is no chemical shift at all. None of the protons will evolve in the rotating frame. That is what is going to happen. So what will happen to couplings? In the spin echo sequence, when we discussed, we clearly mentioned homonuclear spin echo refocuses chemical shifts, but not the couplings. The couplings will continue to evolve following 180 pulse. Okay. So throughout the spin lock continuous period for over several milliseconds, what is going to happen? Chemical shifts do not evolve, but the J couplings start evolving. It as if there is a free precision. If there is a delay, there is a free precision. So it's about the rotation about Z axis. Like that, the J coupling starts evolving. Only chemical shifts do not evolve in the spin locking sequence. So that means this is a mixing will happen. When the chemical shift differences are not there, it is 0. None of them, all the different chemical shifts, inequivalent protons have no chemical shifts at all. That means chemical shifts are 0, but coupling is present. What does it mean? It means you are forcibly creating strong coupling effect. What is we discuss about weak coupling and strong coupling when we discuss about the spin nomenclature. When the chemical shift separation is quite large compared to the coupling, we call them weakly coupled spin system. Whereas when the couplings are comparable to chemical shifts, or chemical shifts are almost 0, much smaller, J over delta, then what is going to happen? In which case, okay, delta by J, if you consider, if delta is very small, it is much smaller than 1, then spin systems are strongly coupled. Now you are forcibly creating a strongly coupled spin system under isotropic condition. So spin lock, what it does is it creates isotropic mixing condition, and there exists an oscillatory exchange of coherence among the coupled spins. Spins are exchanging energy, exchanging coherence, although there are no chemical shifts during the spin lock. So consider an example of a AX spin system, 2 coupled spin system with a coupling constant of J. Then what will happen? Let us say spins are evolving. For half of the coupling, J is, let us say 20 hertz. At exactly 10 hertz, what will happen? Assume A is giving its coherence to X. It will give complete coherence to X in half the J period. In the remaining half, what will happen? It will start coming back. X will start giving back to A. So during the 360 degree complete cycle, there is a exchange going on. It will give the energy, the coherence to the other coupled spin and comes back also in one full 360-degree cycle. This is what is happening in AX spin system. If you take at half JAX, there is a transfer of magnetization from A to X. For the remaining J, half J, it will come back. Of course, this is only for an example of two spins. The propagation of the magnetization among the coupled spin still continues if there are more coupled spins. It is not a simple explanation, and it depends upon the mixing time. I give larger delay. Let us say I have 1, 2, 3, 4 like that, several spins are coupled. If I give small delay, there is a polarization transfer only from 1 to 2. If you give little bit more, it can go from 1 to 2 and 2 to 3, and then bit more it can go to 3 to 4. Like that, depending upon the mixing delay, the polarization transfer among the coupled spin can be extended among all the coupled spins. There is a limit for it. If you extend beyond, what will happen? It will start coming back. There is no use. So that is what, there is an optimization you have to do. Since the magnetization may travel in either direction along a spin chain, it can go here and come back. It can go here, come back. So this transfer of coherence among the coupled spins is bidirectional. It can go forward and come back along the chain. So that means the coherences, if it is established among the coupled partner, is symmetrical again with respect to diagonal. Similar to Cauchy, it is symmetrical with respect to diagonal. So the transfer of magnetization occurs with the mixing time when the spins experience the identical local fields. When it will happen? The transfer of magnetization takes place when the spins experience the identical local field. They behave like, then spins will lose their identity. When there is no identity for the spins, all of them behave like same. So the energy transfer can take place. And what is this condition? This condition is called Hartmann-Hahn. Gamma A into beta 1 of power of RF power of A equal to gamma X into RF power of X. If this condition is matched, it is called Hartmann-Hahn match. Then both the spins, I have taken two examples of A and X spins, both the spins have a same local field and they have lost their identity. There is no chemical shift evolution in this spin lock period. Those simply exchange the coherence. And this type of thing can happen for both homonuclear case and heteronuclear case. The Hartmann-Hahn polarization transfer, if it takes place, it is called homonuclear Hartmann-Hahn, ho-ha-ha. If it is heteronuclear spin, it is called he-ha-ha, heteronuclear Hartmann-Hahn match. So you can do it both for homonuclear case and heteronuclear case. The propagation of magnetization along a chain of coupled spins as a function of spin lock you can explain like this. Let us say A is coupled to B. It goes forward and also come back simultaneously. It is going on. It is bidirectional. So further mixing time it becomes longer. A to B coming back. Similarly go to B, it come back. B to C, it will come back. Similarly you keep extending like C to D, D to E like that. In each step there is a forward exchange of magnetization and backward it gives and also takes back. So there is a cyclic exchange of coherence between the spins. Okay. So in short you will do like this. Let us say this is a spectrum of some molecule, different chemical shifts are there here. Now during mixing what is happening is, if there is no chemical shift, all are like this, but they are coupled among themselves. So you forcibly are inducing strong coupling effect for this. So spin lock also enables sometimes incoherent magnetization transfer. That means need not be through covalent bond, it can be through space also. That is a special type of experiment called nuclear overhauser effect in the rotating frame. We discussed NOE, but we have not discussed ROE. I think if there is a time I will come back and discuss at the end of this course, let me see. But this is called rotating frame overhauser effect, where the polarization transfer takes place not through covalent bond but through space, and that those peaks can also come. Then it will weaken the signal. Toxic peaks become particularly weak, especially in smaller molecule, they are problematic. Sometimes you get exchange peaks. Also you get coupled Cauchy peaks also you get in toxic. So all these things are present, there are various problems. And these sequences over the years, number of toxic sequences have been improved. They are called clean toxic sequence. Okay, that has been improved. So So, now we will look at the 600 megahertz toxic spectrum of a simple molecule 3-heptanon, and this is what it is. Now, it is going to give the energy, or it identify the coupled partners in one experiment. What you have to do in the COSY? You have to go step by step. 1 is coupled to 2, 2 is coupled to 3, it like this you have to keep going like a ladder. Here you do not have to do. In one experiment all entire spin system is identified. For example, here 1 and 2, it forms a spin system, see, and no other thing is coupled here. You will not see any peak either in the F1 dimension or in the F2 dimension, only 2 peaks are there. These 2 are diagonals and only 1 cross peak is there. So, that means 1 and 2 are coupled, that forms a spin system. Now, go to the other one, you see 7 and this is giving to the, this is the diagonal, it gives cross peak, this is another diagonal, it gives cross peak, is another diagonal, it gives peak, one more peak is there here. So, 7 gives polarization to 6, 6 gives to 5, 5 gives to 4. See, it keeps going on like this, and finally entire coupled spin system will give rise to, you will gain polarization. See, here to here, here to here, it keeps on polarization transfer taking place. So, all this thing completely in one vertical line, if you go or go horizontally like this, all spin systems can be identified. They are same. You can see there are different chemical shifts along F2 and same along F1, they all form a spin system. So, you can have vertical lines or horizontal lines, you write either way, they are all coupled spin systems. So, 2 spin systems can be easily identified by this method. This is what the Toxi does. It identifies coupled partners for each spin system in one single experiment. So, let us compare Toxi and COSY. This is a COSY and this is Toxi for the same molecule. Here just now we understood this forms 1 and this forms 1, 2 coupled spin system here identified in one shot. Here what we have to do? This goes systematically 1 to here, then here, here, then here, here, like that it goes. Whereas it is simply identified in one shot here. Here again you have to come here and identify. So, 2 spin systems to identify in COSY, especially in this case 1 and 2 are coupled is easy, but then 4 protons are coupled, you have to go in a ladder like this, 4 steps, because each time you identify only the immediate neighbor, whereas Toxi identifies in single experiment. That is an advantage. Okay. With this we will go to, there are a number of Toxi experiments called clean Toxi sequences. Those who are interested can go to the literature, there is no time to cover everything. We will go to the heteronuclear correlation experiment. It is again a correlation experiment. Instead of homonuclear, we are correlating 2 different heteronuclei. For example, we can correlate proton to carbon, proton to nitrogen, carbon to anything, any two heteronuclei we can correlate. So, in this case the chemical shift connectivity between 2 heteronuclei are established. What did we do in COSY? Identified 2 coupled partners, that chemical shifts are on the diagonal, which we identified very easily. So, we could identify, it establishes the chemical shift connectivity among homonuclear case spins in COSY. In this case we are identifying or establishing chemical shift connectivity between 2 heteronuclei. That is why it is called heteronuclear correlation experiment, or called HETCOR, heteronuclear correlation spectroscopy. Thus, in a simplest form, HETCOR looks like this. Very simple experiment. A 90-degree pulse, before that there is a preparation period, here everything is done, and then it is in thermal equilibrium. 90-degree pulse rotates the magnetization into XY plane. Here it will start evolving. It evolves precisely in the XY plane for a period T1, evolves under the influence of the chemical shift of protons and also J coupling between carbon and proton. Here there is inept mixing. So, because antiphase character J coupling creates antiphase signals. So, there is a transfer of polarization from proton to carbon takes place here using an inept sequence. Okay. And then that happens and mixing transfer signal here, inept creates transfer the polarization from one proton to carbon, and simultaneously when you apply 90-degree pulse on both, magnetization transfer is taking place, and then it converts last pulse 1H magnetization, the antiphase it with respect to attached carbon 13, the inert sequence, and then we transfer the magnetization to proton and start collecting the proton signal. Of course, we can have a decoupled version and coupled version. Simply you understand, in a short form I want to say one thing. What we are going to do here is, in a simple way, you bring the magnetization to expel plane, allow it to evolve, bring isotropic mixing and transfer the magnetization from carbon to proton, start detecting the proton. You can also do the decoupling. This is the simple experiment for HETCAR. In brief, it gives information on which carbon is attached to which proton. You can also do by, it is done by inverting the proton population and varying the transfer of polarization, proton polarization to carbon 13 during T1. That is what happens in the T1 period, although we did not discuss in stretch. So, you can have the decoupled version, various variants are there, but nowadays we do not go into that, we will go to HSQC, that is why I do not touch upon it. I just wanted to tell you this is, there is a heteronuclear correlation experiment. In a different way we can do that. Look at this molecule. You have simple molecule, there is one in this axis is proton, in this axis carbon 13. If you go along this axis you get the proton chemical shift, you go along this axis you get carbon 13 chemical shift. So, it says proton chemical shift for 1 is here, carbon chemical shift is here. So, simultaneously you can detect both the nuclei. It correlates chemical shift of 2 heteronuclei. So, similarly for this 5, 2, 3 and 4 like this. You can identify different chemical shifts of coupled heteronuclei which are coupled. Okay. And one interesting thing is, if a peak like this there, it does not give any cross peak here, that means they are usually quaternary carbons like this which are not protonated or non-protonated carbon, ipso carbon like that. Such carbons, if it is in carbon 13 proton HSQC I am talking heteronuclear correlation, if there is no cross peak, that means those carbons are not attached to protons. Remember this. Of course, we can start seeing this for a bigger molecule also. There is no time to go through that, we will not worry about that. We will go to the next experiment called inverse spectroscopy. That is previous slide is only just showing for a bigger molecule how we can establish correlation of chemical shift of carbon and proton for a bigger molecule. We will introduce a new technique called inverse spectroscopy. What is inverse spectroscopy? Is a direct detection of X nuclei is less sensitive. Carbon 13, as I told you right from the first class, previous course, this course we have discussed, sensitivity of carbon is nearly 64 times smaller than that of proton. In taking into account the natural abundance, it is 6400 times less sensitive relative to proton. Hence, direct detection takes lot of time, especially if you go to a bigger molecule contain large number of dilute spins like that, less sensitive nuclei carbon. On the other hand, if we do inverse detection by taking the magnetization of the proton, give it to carbon and detect carbon, or take it back to proton and detect in the indirect way, there is a tremendous gain in the sensitivity if you detect the proton. We can do that. Directly detect proton. What we have to do is, this takes enormous amount of time, take the carbon signal, give it to proton and take it back to from proton to carbon. Okay. Then in between something has happened. So, we can see during this process there is some transfer of coherence. So, direct detection takes 15 to 20 minutes, indirect detection where you transfer the magnetization from proton to carbon. Of course, this heteronuclear correlation experiment there are several ways. You can give from carbon to proton, take back to proton, proton to carbon, take it back to proton, and so there are 3, 4 or 5 different approaches are there. So, generally what is adapted in the inverse experiment is energy coherence is transferred from proton to carbon, then carbon to taken to back to proton, and proton is detected while decoupling the carbon 13. But simply remember, the inverse detection is very advantageous, because direct detection of this thing takes 15 to 20 hours, whereas inverse detection just take 1 to 2 hours. Enormous saving in the time, because there is a gain in the sensitivity. It takes advantages of reverse inept for transfers, first proton to carbon and then back to proton, which is easy to detect. And you can do broadband decoupling simultaneously. You can apply varieties of pulse sequences are there for decoupling, Waltz, GARP, MLEV, etc. We can discuss those things. So, our broadband CW continuous wave decoupling, that is commonly I told you about heteronuclear decoupling, that can be adapted. Okay. So, in the using 2D inverse detection, in the 2-dimensional experiment, detection dimension is always proton. Why? It is advantageous to detect proton which is highly abundant spinless and high gamma nucleus compared to carbon 13. That is why in the inverse experiment detection dimension is proton, TT is proton. In between you do some jugglery, take the magnetization, give it a dilute spin, take it back and all those things you do. But final detection is proton, while decoupling carbon or a nitrogen, whatever the nuclei. So, there are various experiments like this identified. It is called HMQC, HSQC, HMBC, etc. This is called heteronuclear multiple quantum coherence, heteronuclear single quantum coherence and heteronuclear multiple bond coherence. There are n number of such these things are there, varieties of modifications of experiments of these things are there. Okay. So, we quickly look at HSQC and HMBC today. Of course, HMQC gives similar information like HSQC, but little subtle modification is there. We will not go to HMQC, but HSQC and HMBC we will discuss little bit more with some examples. So, how does 2D inverse being done, inverse detection? It is all these experiments have a direct correlation experiment which there is a direct correlation. For example, I told HETCAR, where directly you can detect proton in one dimension, carbon in one other dimension, heteronuclear correlation of two different heteronuclear spins, chemical shift correlation like heteronuclear COSY. The same thing inverse version is called HSQC. This is faster. This will take 15 to 20 hours, this will take 1 to 2 hours. Similarly, HMQC. Similarly, we have HMBC, inverse experiment. This direct experiment for this is called COLAC, correlation of long range coupling, long range correlation. Long range coherences can be correlated. That is, so HMQC inverse experiments have some of the direct experiments also, one to one analogs you can find out. So, HSQC, HMBC, all those things make use of multiple quantum pathway, HMBC and HSQC during evolution time, while HSQC makes use of single quantum pathway and it uses inept also during evolution time. Very important thing. These two experiments makes use of multiple quantum pathway, HSQC also single quantum pathway, and also it uses inept during evolution time. So, what HSQC gives is connectivity between directly coupled proton analogous to HETCAR. See, if I have so many carbons in equivalent, I can say this carbon is coupled to this proton, this carbon is coupled to all this direct correlation information it gives. So, it based on direct coupling, one bond proton carbon coupling strength, which is approximately of the order of 150 hertz. So, you can use that and then set up the experiment. If your mixing time is set for this, it so happens you will establish the correlation among directly coupled carbon proton this heteronuclei. HMBC gives connectivity between remotely coupled nuclei. Same thing if I want to do, for example, let us take this carbon. Instead of giving this one correlation to this, HSQC does this. From this carbon to this carbon, which is 2 bonds away, this is called long bond multiple bond correlation. This HMBC gives. This HSQC gives, whereas this to this HMBC gives. Similarly, this to this HMBC gives. This HMBC gives this also, and it can go to even 3 bond, 4 bond away. For example, this can give. So, HMBC gives multiple bond correlation, HSQC gives single quantum directly bonded. So, with this we will come back and then discuss something about, time is getting up, we will come back and discuss HSQC bit more, take some examples, analyze HSQC spectra and some HMBC, and afterwards we can also go for some other experiment like K-resolved and if possible inadequate, all those experiments we can consider. So, we will come back and see quickly, but today we have discussed about correlation experiments in homonuclear case and heteronuclear case, direct detection like COSY, TOXY and HETCAR. TOCSY gives a direct connectivity among all the coupled partners in a single experiment. COSY establishes connectivity, chemical shift connectivities among the coupled partners, immediate coupled partners, immediate neighbor. Heteronuclear does a similar experiment, direct detection, whereas it is directly bonded proton carbon can be identified. And this direct detection takes enormous amount of time. The improved version is there, that is called inverse detection, where the magnetization of the proton is given to carbon and taken back to proton, and proton is detected. In this process we can establish the correlation between proton and carbon heteronuclei also, but this inverse detection is more sensitive and is much faster. So there are various experiments for inverse and direct detection. There is one-to-one correlation is there for names. HETCOR is equivalent to HSUC, COLOC is equal to HMBC, etc. So with this I am going to stop here. We will come back and continue take example of HSQC analysis, etc. in the next class. Thank you.